Previously, you have learnt about alpha, beta, and gamma emissions by relatively. From the curve showing the variation in average binding energy versus the mass number A, we have seen that elements with A ranging from 30 to 170, like iron, cobalt, etc., have relatively high binding energy per nucleon, EBN, and of nearly 8 MeV. The nuclei with average binding energy of approximately. From the same curve, we observe that the nuclei with mass number less than 30 and greater than 170 have binding energy per nucleon. This implies that when tightly bound nuclei transform into relatively less tightly bound nuclei, when such nuclear transformations occur, an enormous amount of nuclear energy is released, as in the case of nuclear fission or nuclear fusion, which you will learn in detail later. Let us now compare this energy to that which is released when we use conventional energy resources like coal, petroleum, etc. Conventional energy resources release energy through chemical reactions. For example, when 1 kilogram of coal is burnt, the amount of energy released is about 10 to the power 7 joule. But the nuclear energy released in the fission of 1 kilogram of uranium is about 10 to the power 14 joule, which is a million times greater than that released by a conventional source of energy. Therefore, the energy obtained from a nuclear source is considerably enormous compared to that obtained from an equivalent mass of conventional source of energy. At the same time, we have to remember that since a large amount of radiation is involved in such nuclear processes, they are extremely hazardous if not handled carefully. Let us now look at the nuclear processes which release such enormous amounts of nuclear energy. An Italian-American physicist, Enrico Fermi, found that when neutrons are bombarded onto various elements, new radioactive elements may be produced. For example, when cobalt-59 is bombarded with neutrons, it captures a neutron and transforms to cobalt-60, which is radioactive in nature. But when a uranium target is bombarded with a neutron, it splits into two almost equal fragments, accompanied by the release of a large amount of energy. This nuclear process is called nuclear fission. Let us look at an example of nuclear fission. When uranium-235 absorbs a neutron, it becomes unstable and undergoes nuclear fission. The fission products are barium-144, krypton-89, and 3 neutrons. It is also observed that in such type of fission, the products need not always be barium and krypton. The fission products of uranium-235 can also be antimony-133, niobium-99, and 4 neutrons, or xenon-140, strontium-94, and 2 neutrons. Thus, we see that nuclear fission involves the release of neutrons along with other products which may vary. We also see that the number of neutrons released also varies depending on the other products of fission being released. Let us now estimate the amount of nuclear energy or the value of Q being released during fission. Consider a nucleus of mass number A equal to 240 undergoing a nuclear fission. From the average binding energy versus mass number curve, we observe that for A equal to 240, the average binding energy is 7.6 MeV. Therefore, the total binding energy for this nuclide is 240 into 7.6, which is equal to 1824 MeV. Let us now assume that this nucleus undergoes nuclear fission and forms into two fragments with atomic mass number A equal to 120 each. From the graph, we find that for nuclei with A equal to 120, average binding energy is about 8.5 MeV. So, the total binding energy for the product nuclides is equal to 2 into 120 into 8.5, that is 2040 MeV for the two products put together. This shows that when a single nucleus of mass number 240 splits into two nuclei, the gain in binding energy is 2040 minus 1824, which is equal to 216 MeV. This energy is extremely large and is about 1,000,000 times larger than the conventional energy sources like wood, coal, petroleum, etc. The enormous amount of energy, which is the disintegration energy of the fission process, initially appears as the kinetic energy of the fission products and the neutrons, and finally is transferred as heat into the surrounding matter. Thus, a nuclear fission process generates an enormous amount of heat energy. It is also observed that nuclear fission products are highly rich in neutrons and are unstable and radioactive. They emit beta particles in succession until they reach a stable end product. Put to proper use, this nuclear energy can be used to generate electricity in a nuclear power plant. On the other hand, high levels of energy and radiation in an atomic bomb can be obtained by an uncontrolled nuclear fission, causing grave damage to nature and mankind. Thus, the same fission reaction is the base for the useful nuclear reactor as well as the destructive atomic bombs. It depends on us how we use